This is a glossary of arithmetic and Diophantine geometry in mathematics, areas growing out of the traditional study of Diophantine equations to encompass large parts of number theory and algebraic geometry. Much of the theory is in the form of proposed conjectures, which can be related at various levels of generality. Diophantine geometry in general is the study of algebraic varieties V over fields K that are finitely generated over their prime fields, including as of special interest number fields and finite fields, and over local fields. Of those, only the complex numbers are algebraically closed. Over any other K, the existence of points of V with coordinates in K is something to be proved and studied as an extra topic. Even knowing the geometry of V, arithmetical or arithmetic geometry is a field with a less elementary definition. After the advent of scheme theory, it could reasonably be defined as the study of Alexander Grothendieck's schemes of finite type over the spectrum of the ring of integers Z. This point of view has been very influential for around half a century. It has very widely been regarded as fulfilling Leopold Kronecker's ambition to have number theory operate only with rings that are quotients of polynomial rings over the integers. In fact, scheme theory uses all sorts of auxiliary constructions that do not appear at all finitistic, so that there is little connection with constructivist ideas as such. That scheme theory may not be the last word appears from continuing interest in the infinite primes, which do not come from prime ideals as the p-adic numbers do. ABC conjecture. The ABC conjecture of Mazur and Easterley attempts to state as much as possible about repeated prime factors in an equation A plus B equals C. For example, 3 plus 125 equals 128, but the prime powers here are exceptional. Array-Love class group. The Array-Love class group is the analog of the ideal class group or divisor class group for Array-Love divisors. Array-Love divisor. In Array-Love divisor on a global field is an extension of the concept of divisor or fractional ideal. It is a formal linear combination of places of the field with finite places having integer coefficients and the infinite places having real coefficients. Array-Love height. The Array-Love height on a projective space over the field of algebraic numbers is a global height function with local contributions coming from Fubini study metrics on the Archimedean fields and the usual metric on the non-Archimedean fields. Array-Love theory. Array-Love theory is an approach to arithmetic geometry that explicitly includes the infinite primes. Arithmetic of Abelian varieties. See main article. Arithmetic of Abelian varieties. Artinel functions. Artinel functions are defined for quite general Galois representations. The introduction of Attribution homology in the 1960s meant that Hassavile L functions could be regarded as Artinel functions for the Galois representations on L-adic cohomology groups. B. Bad reduction. C. Good reduction. Birch-Swinnerton-Dyer conjecture. The Birch-Swinnerton-Dyer conjecture on elliptic curves postulates a connection between the rank of an elliptic curve and the order of pole of its Hassavile L function. It has been an important landmark in Diophantine geometry since the mid-1960s, with results such as the Cotes-Walz theorem, Gross-Zagier theorem, and Colli-Vagens theorem. Bombieri-Lang conjecture. Enrico Bombieri, Serge Lang and Paul Vodta and Piotr Blas have conjectured that algebraic varieties of general type do not have Zariski-dense subsets of K rational points. For K a finitely generated field, this circle of ideas includes the understanding of analytic hyperbolicity and the Lang conjectures on that, and the Vodta conjectures. An analytically hyperbolic algebraic variety V over the complex numbers is one such that no holomorphic mapping from the whole complex plane to it exists. That is not constant. Examples include compact Riemann surfaces of genus G greater than 1. Lang conjectured that V is analytically holomorphic if and only if all subvarieties are of general type. C. Canonical height. The canonical height on an abelian variety is a height function that is a distinguished quadratic form. See any acute RON Tate height. Chabauty's method, based on p-adic analytic functions, is a special application but capable of proving cases of the Mordell conjecture for curves whose Jacobian's rank is less than its dimension. It developed ideas from Thoralf Skolum's method for an algebraic torus. Cotes-Walz theorem. The Cotes-Walz theorem states that an elliptic curve with complex multiplication by an imaginary quadratic field of class number 1 and positive rank has L function with a 0 at s equals 1. This is a special case of the Birch and Swinnerton-Dyer conjecture. Crystalline cohomology. Crystalline cohomology is a p-adic cohomology theory in characteristic P, introduced by Alexander Grothendieck to fill the gap left by et al. Cohomology, which is deficient in using mod P coefficients in this case. It is one of a number of theories deriving in some way from Twerks method, and has applications outside purely arithmetical questions. D. Diagonal forms. Diagonal forms are some of the simplest projective varieties to study from an arithmetic point of view. Their local zeta functions are computed in terms of Jacobi sums. Waring's problem is the most classical case. Diophantine dimension. The Diophantine dimension of a field is the smallest natural number k, if it exists, such that the field of is class Ck. That is, such that in any homogeneous polynomial of degree d in n variables has a non-trivial zero whenever n greater than dk. Algebraically closed fields are of Diophantine dimension 0, quasi-algebraically closed fields of dimension 1. Discriminant of appoints. The discriminant of a point refers to two related concepts relative to a point P on an algebraic variety V defined over a number field K. The geometric discriminant D and the arithmetic discriminant, defined by Voigtler. The difference between the two may be compared to the difference between the arithmetic genus of a singular curve and the geometric genus of the desingularization. The arithmetic genus is larger than the geometric genus, and the height of a point may be bounded in terms of the arithmetic genus. Obtaining similar bounds involving the geometric genus would have significant consequences. Twerks method. Bernard Twerk used distinctive methods of p-adic analysis, p-adic algebraic differential equations, causal complexes and other techniques that have not all been absorbed into general theories such as crystalline cohomology. He first proved the rationality of local zeta functions, the initial advance in the direction of the Weil conjectures. Et al. Cohomology. The search for a Weil cohomology was at least partially fulfilled in the et al. Cohomology theory of Alexander Grothendieck and Michael Artin. It provided a proof of the functional equation for the local zeta functions, and was basic in the formulation of the Tate conjecture and numerous other theories. F. Falting's height. The Falting's height of an elliptic curve or abelian variety defined over a number field is a measure of its complexity introduced by Faltings in his proof of the Mordell conjecture. Fermat's last theorem. Fermat's last theorem, the most celebrated conjecture of Diophantine geometry, was proved by Andrew Wiles and Richard Taylor. Flacco homology. Flacco homology is, for the school of Grothendieck, one terminal point of development. It has the disadvantage of being quite hard to compute with. The reason that the flat topology has been considered the right foundational topos for scheme theory goes back to the fact of faithfully flat descent. The discovery of Grothendieck that the representable funct is a sheaves for it function field analogy. It was realized in the 19th century that the ring of integers of a number field has analogies with the affine coordinate ring of an algebraic curve or compact Riemann surface, with a point or more removed corresponding to the infinite places of a number field. This idea is more precisely encoded in the theory that global fields should all be treated on the same basis. The idea goes further. Thus elliptic surfaces over the complex numbers also have some quite strict analogies with elliptic curves over number fields. Geometric class field theory. The extension of class field theory style results on abelian coverings to varieties of dimension at least 2 is often called geometric class field theory. Good reduction. Fundamental to local analysis in arithmetic problems is to reduce modulo all prime numbers P, or, more generally, prime ideals. In the typical situation, this presents little difficulty for almost all P. For example, denominators of fractions are tricky. In that reduction, modulo a prime in the denominator look like division by zero, but that rules out only finitely many P per fraction. With a little extra sophistication, homogeneous coordinates allow clearing of denominators by multiplying by a common scalar. For a given single point, one can do this and not leave a common factor P. However, singularity theory enters. A non-singular point may become a singular point on reduction modulo P, because the Zariski tangent space can become larger when linear terms reduce to zero. Good reduction refers to the reduced variety having the same properties as the original, for example, an algebraic curve having the same genus, or a smooth variety remaining smooth. In general, there will be a finite set S of primes for a given variety V, assumed smooth, such that there is otherwise a smooth reduced VP over Z, PZ. For abelian varieties, good reduction is connected with ramification in the field of division points by the Eni-Akutaro-Enog-Shafarevich criterion. The theory is subtle, in the sense that the freedom to change variables to try to improve matters is rather unobvious. See Eni-Akutaro-N model. Potential good reduction. Take curve, semi-stable abelian variety, semi-stable elliptic curve, Sertate theorem. Groth-Ndike-Katz conjecture. The Groth-Ndike-Katz p-curvature conjecture applies reduction modulo primes to algebraic differential equations to derive information on algebraic function solutions. It is an open problem as of 2005. Update. The initial result of this type was Eisenstein's theorem. Hasse principle. The Hasse principle states that solubility for a global field is the same as solubility in all relevant local fields. One of the main objectives of Diophantine geometry is to classify cases where the Hasse principle holds. Generally, that is for a large number of variables, when the degree of an equation is held fixed. The Hasse principle is often associated with the success of the Hardy-Littlewood circle method. When the circle method works, it can provide extra, quantitative information such as asymptotic number of solutions. Reducing the number of variables makes the circle method harder, therefore failures of the Hasse principle, for example for cubic forms in small numbers of variables, are at a general level connected with the limitations of the analytic approach. Hasse-Weil L function. A Hasse-Weil L function, sometimes called a global L function, is an Euler product formed from local zeta functions. Langland's philosophy is largely complementary to the theory of global L functions. Height function. A height function in Diophantine geometry quantifies the size of solutions to Diophantine equations. Classical or naive height is defined in terms of ordinary absolute value on homogeneous coordinates. Heights were initially developed by André Weil and D.G. Northcott. Innovations around 1960 were the Eni-Akutaro-N Tate height and the realization that heights were linked to projective representations in much the same way that ample line bundles are in pure geometry. Hilbertian fields. A Hilbertian field K is one for which the projective space is over K and not thin sets in the sense of Jean-Pierre Serre. This is a geometric take on Hilbert's irreducibility theorem, which shows the rational numbers are Hilbertian. Results are applied to the inverse Galois problem. Thin sets are in some sense analogous to the megasets of the back-category theorem. Igusa zeta function. An Igusa zeta function, named for Geometry Igusa, is a generating function counting numbers of points on an algebraic variety modulo high powers Pn of a fixed prime number P. General rationality theorems are now known, drawing on methods of mathematical logic. Infinite descent was Pierre de Fermat's classical method for Diophantine equations. It became one half of the standard proof of the more Delvile theorem, with the other being an argument with height functions. Descent is something like division by 2 in a group of principal homogeneous spaces, in more modern terms in a Galois cohomology group which is to be proved finite. See Selma group. Iwasawa theory builds up from the analytic number theory and Stickelberger's theorem as a theory of ideal class groups as Galois modules and p-adic L functions. In its early days in the late 1960s it was called Iwasawa's analog of the Jacobian. The analogy was with the Jacobian variety J of a curve C over a finite field F, where the finite field has roots of unity, aided to make finite field extensions F. The local zeta function of C can be recovered from the points J, as Galois module. In the same way, Iwasawa added Pn power roots of unity for fixed P and with n infinity, for his analog, to a number field K, and considered the inverse limit of class groups, finding a p-adic L function earlier introduced by Kubota and Leopold. K-theory. Algebraic K-theory is on one hand a quite general theory with an abstract algebra flavor, and, on the other hand, implicated in some formulations of arithmetic conjectures. See for example Birch-Tate conjecture, Lichtenbaum conjecture. Linear torus. A linear torus is a geometrically irreducible Zariski closed subgroup of an affine torus. Local zeta function. A local zeta function is a generating function for the number of points on an algebraic variety V over a finite field F, over the finite field extensions of F. According to the Weil conjectures, these functions, for non-singular varieties, exhibit properties closely analogous to the Riemann zeta function, including the Riemann hypothesis. Manny-Mumford conjecture. The Manny-Mumford conjecture, now proved by Michel Reynaud, states that a curve C and its Jacobian variety J can only contain a finite number of points that are of finite order in J, unless C equals J. Mordell conjecture. The Mordell conjecture is now the Faltings theorem, and states that a curve of genus at least 2 has only finitely many rational points. The Uniformity Conjecture states that there should be a uniform bound on the number of such points, depending only on the genus and the field of definition. Mordell-Lang conjecture. The Mordell-Lang conjecture is a collection of conjectures of Serge Lang unifying the Mordell conjecture and Manny-Mumford conjecture in an abelian variety or semi-abelian variety. Moore-Delvile theorem. The Moore-Delvile theorem is a foundational result stating that for an abelian variety A over a number field K, the group A is a finitely generated abelian group. This was proved initially for number fields K, but extends to all finitely generated fields. Mordelic variety. A Mordelic variety is an algebraic variety which has only finitely many points in any finitely generated field. Naive height. The naive or classical height of a vector of rational numbers is the maximum absolute value of the vector of coprime integers, obtained by multiplying through by a lowest common denominator. This may be used to define height on a point in projective space over Q, or of a polynomial, regarded as a vector of coefficients, or of an algebraic number, from the height of its minimal polynomial. N-acute-RO end symbol. The N-acute-RO end symbol is a bimultiplicative pairing between divisors and algebraic cycles on an abelian variety used in Néron's formulation of the N-acute-RO end. Tate's height as a sum of local contributions. The global any acute RON symbol, which is the sum of the local symbols, is just the negative of the height pairing. Any acute RON Tate height. The any acute RON Tate height on an abelian variety A is a height function that is essentially intrinsic, and an exact quadratic form, rather than approximately quadratic with respect to the addition on A as provided by the general theory of heights. It can be defined from a general height by a limiting process. There are also formulae, in the sense that it is a sum of local contributions. Neven linear invariant. The Neven linear invariant of an ample divisor D on a normal projective variety X is a real number which describes the rate of growth of the number of rational points on the variety with respect to the embedding defined by the divisor. Ordinary reduction. An abelian variety A of dimension D has ordinary reduction at a prime P if it has good reduction at P, and in addition the P torsion has rank D. Q. Quasi-algebraic closure. The topic of quasi-algebraic closure, i.e., solubility guaranteed by a number of variables polynomial in the degree of an equation, grew out of studies of the Brouwer group and the Chevalier-Warning theorem. It stalled in the face of counterexamples, but see X-Kochen theorem from mathematical logic. R. Reduction modulo a prime number or ideal. C. Good reduction. Replete ideal. A replete ideal in a number field K is a formal product of a fractional ideal of K and a vector of positive real numbers with components indexed by the infinite places of K. A replete divisor is an irregular divisor.